Welcome viewers. In this video we are going to do design of a transmission line tower foundation type 1 pad and chimney using Indian standard. This is part 6 and final part with this type of series. And here we are going to do design of a base slab followed by the earlier part 5 we had done the design of a base slab for compression and uplift reinforcement. In this we are going to do the same design of base slab, but in this we are going to do shear and bond stress check. Shear means it is a one-way shear and a two-way shear. Two-way shear is nothing but it is a punching shear. So the two shear stress and the bond stress check we are going to do with this part 6. So this is a final. With that, entire design of transmission line tower foundation type 1 pad and chimney using Indian standard get completed. So before going to watch this video, we request you to watch our previous video. Start from part 1. We had seen how to extract the tower geometry from the structure design and the design foundation loads, followed by that soil parameters, foundation geometry required for design of this type 1 pad and chimney transmission line tower foundation. Also we seen that uplift resistance check in part 1 and part 2, which is followed by the part 1 which covered check for bearing capacity for the entire transmission line tower type 1 foundation. Followed by in part 3 we had seen how to do sliding check, overturning check. In part 4 we had seen a design of a chimney. In the part 5 we had designed the base slab reinforcement in both compression and uplift zone. So this is part 6. Also we had also designed the stub angle in American standard. We had also given those explanation in another video. Another video which is in that we had discussed about the type of various other type of transmission line tower foundation and the philosophy to calculate the transmission line tower foundations. So all this video link are given in the description. You can look into that before watching to this video. Let me look into that Excel calculation which we had already prepared and discussed. So here are the 3 final steps we need to look into that. This part 6 video of foundation type 1 pad and chimney for transmission line tower foundations. So these 3 steps we had not seen in our previous video 5. So these 3 steps are included in the foundation base slab design. We had designed compression reinforcement and uplift reinforcement in our part 5. Now in this we will be looking into that one-way shear, two-way shear check, and finally the bond stress check. So before going to detailed calculation, we need to understand the difference between the one-way shear and the two-way shear. So let me look into this picture showing in the right hand side plan and elevations. So this area, this first rectangular cover, or it should be a square because we have considered the square foundation, but due to this rough sketch it is looking like rectangular. So let me assume these are all shapes in as a square. So this is a column size and this is a drop size. You can see in that foundation geometry. So we are considering this shape at XX, that including the base slab, and second section we are considering the base slab including the top tapered level to the bottom base level. This is a Y and this is a X. So these two sections we are going to check both the one-way shear and two-way shear, that is punching shear. So that first inner circle or inner square rectangular which we had seen is this chimney size. Second one is the 1.5 meter drop slab, and the third and final one rectangular or square shape is a base slab size at 5 meter. So these are the shapes we need to consider. So this is the 700 mm chimney box. This box refers to the drop of 1.5 meter which we had considered in our foundation geometry. So this drop is that second rectangular box, and the third one is the whole base slab that is a 5 meter we had considered in our geometry. So this 5 meter is a third box. So these views are in plan, and coming to the elevations, so this is a base slab and this is a drop slab, this is a chimney. So these are the three parts included in various sections for both one-way and two-way shear. For the explanation purpose, we had made a rough sketch. So coming to the section XX, this XX refers both the thickness of draft and the drop and the base slab. And section YY we had considered here in the foundation geometry, section YY and X. So that section YY will covers the thickness only on the base slab, that including the tapered slab. So here we are not going to detail work on the tapered slab and the flat slab. So we are considering the both slab in a single stage. So these are the section at XX and YY. So now let we look where how the one-way shear force is going to act. So look into that section. Due to the upward bearing pressure and the vertical downward reactions from the column and the drop slab, there will be one shear which is going to act in the connection point. So there are two method of shears will act. One is like this, one side shear will be there. You might have experienced some of the crack will be formed in between the connection area of drop wall and chimney with the base slab. So that crack is mainly due to the one-way shear. So that one-way shear will occurs at a distance from the column face plus the effective depth of the slab. So we had already calculated the effective depth D1 here in the reinforcement calculation. You can see here D1 refers to effective depth at section XX and D2 refers to effective depth at YY. Those values are 476 and 276 mm respectively. So that we need to consider in our both one-way shear and two-way shear checks. So effective occurrence of shear is at D, effective depth from the column face. So that is what we are calculating here. So that design bearing pressure which is coming from the base slab in upward direction is 0.037 Newton per millimeter square, which we had calculated already for the reinforcement design calculations. So here you can see that value. With that, we need to calculate the shear force. As we know that the shear force is going to act in the effective area like from the face of the column. So we need to consider this span alone. That is 5 meter is a total width, and we need to deduct this column and the whole divided by 2, we will be getting this area. So that is what done here, and that value we need to deduct from the effective depth, because our effective shear will occur somewhere here, because you can see in that section view. So when we are applying the D1 dimension from the face of the column with the inclined 45-degree shear plane, so then the shear plane will show you the effective shear distance will occur somewhere away from the face of the column at a distance of D1. D1 is the effective depth at XX. So this is the effective span we need to consider for shear force calculations. So the D1 we need to deduct from that. So this, the effective shear force distance will be occur somewhere here. So that this we are going to multiply with our design bearing pressure. So likewise, these are the equations and with the values. So the L is a 5 meter total span, and 700 is the cross section area, cross section dimension, size of the column or chimney. that divided by 2 minus the D1 is effective depth which we had calculated already for reinforcement design, and the whole we are multiplying with the stress value, bearing pressure stress value, we are getting a bearing shear force in Newton. So here we have considered only 1 meter, so that is 1000 mm. So this is for 1000 mm width or per mm width. So we need to find out the shear stress. So here already we have considered 1 meter. So again for width we need to consider here also 1 meter. If we need to take the whole length, that is 5 meter also, it is not an issue. We need to apply the 5 meter here, and the same way the width here also we need to apply the 5 meter, that is 5000 mm and 5000 mm here. It's not a problem, both the way we can work on that, but only the effective depth will be vary here. In section XX we need to consider the D1 effective depth. So applying this, we are getting the shear stress as 0.131 Newton per millimeter square. This is actual or activating shear stress due to the external force or the design bearing pressure. Now we need to check with the concrete bearing or shear stress resistant considering the reinforcement. So this is a percentage of steel reinforcement we had calculated. We already designed the reinforcement here and find out in for bending moment section at XX we are having 2813.44 millimeter square as a reinforcement, main reinforcement. So that divided by the effective area which we are having 5000, the whole width divided by the effective depth at section XX. So applying that we are getting 0.119 percentage of steel reinforcement. So based upon the IS 456 table 19, you can see in the right hand side page number 74. So from this table we need to pick according to the grade of concrete. So grade of concrete we already consider as M25 in our basic input. So here 0.15, if it is less than, the percentage of steel reinforcement is less than 0.15, less than or equal to, then we need to consider 0.29. So our case it is 0.119, which is less than 0.15. So we are considering 0.29 Newton per millimeter square as a shear allowable shear stress. So this allowable shear stress is greater than the actual shear stress, which is 0.131. So hence this section XX is safe in one-way shear. Now next we need to check with the shear stress with the section YY. So here the section YY, only the things which we need to change is this effective length. So here the shear force will act in L minus L1 by 2. L1 is nothing but the 1.5 meter, the drop width which we had considered here. So the drop width is 1.5, the L is 5000 here. So that we are doing the same like in XX section. We need to do only the thing change is here it is L1, here it is CL. So that divided by 2 minus the here the effective depth, we need to consider the effective depth at section YY which we had calculated for reinforcement design. So here you can see D2 is 276 mm. So that we need to apply here because the effective depth at YY is D2 where the shear effective shear is going to act. So again here 1000 we are considering instead of considering the whole width, or else we can do the consider the whole width also 5 meter, and that same width to be considered here also in order to calculate the shear stress. So likewise we are applying this and we are getting the shear stress as 0.198 Newton per millimeter square. Similar like for section YY we had calculated the reinforcement here as 3215. So you can see here this compression reinforcement we had calculated for section YY in last video part 5. In that 3215 is our reinforcement. So again we are dividing those with the effective depth and with total width. We are getting 0.233 percentage of steel reinforcement. Again we need to refer the table 19. So for grade of concrete, here in this 0.25 and 0.15 is percentage of steel reinforcement is there in our right hand side PDF file 456 Indian standard. So in that our value percentage of steel reinforcement is 0.233%. So it is in between this 0.15 and 0.25. So we need to do some interpolation calculation between this 0.36 and 0.29 in line with the 0.15 and 0.25 percentage of steel reinforcement. So by applying this, we are getting allowable shear stress is 0.348, which is greater than the required or actual shear stress 0.192. Hence, this is safe. So this is what the one-way shear check. Next, we will go to the check for two-way shear. Check for two-way shear. So first, we will understand what is a two-way shear. So on the right hand side you can see the picture, the plan and elevation of the same. So two-way shear will act around the column circumferential area. So that distance will be the D, that is effective depth from the column face. So this area is subject to two-way shear. So in order to find the area, the column length or size we need to consider plus the 2 times half of D1 by 2. D1 is the effective depth. So half of the effective depth around the circumferential of column, this two-way shear will act. So you can see here in the elevation also. So this portion, this two portion is subject to two-way shear. So the two-way shear is nothing but the punching shear. So if we are going to do any punching on the paper using the punching machine, there will be some stress around the circumferential will occur so that the paper can make a hole after pressing the punching press. So this kind of actions only we are calling as a two-way shear or punching shear. So for that calculation, the design bearing press which we already calculated, design bearing pressure in while calculating the reinforcement, we had calculated as 0.37 Newton per square mm. So from that we need to derive the shear forces. So here that L square is the total length minus CL plus D1 square. So D1 divided by 2 into 2 will be D1. So that D1 we are adding with the area of size of the column so that we can able to get this length alone. So the whole rectangular square minus this length, we can able to get the area of this portion. So that is what applied here, and we are getting shear forces 873830 Newton, that we are converting into shear stress. So there are 4 area you can see here, 1 2 3 4. So we are dividing that with 4 into 467 is the effective depth which we had calculated already in our last part video, effective depth. So that into area. So the length we are adding as CL is the size of the column plus 2 times D1 by 2. So it is D1. So again we are considering the effective depth which we had calculated during our reinforcement calculation. So now the shear stress is 0.391 Newton per millimeter square. So according to that 456 we need to check. So to find the allowable shear stress we need to refer class 31.6.3.1 of IS 456 2000. So you can see on the right hand side the code IS 456. So to refer the class 31.6.3.1 we need to go for page number 59. So here is the page number 59. So here it is explained the permissible shear stress is Ks into tau c. So to find the value of Ks, so Ks it is defined as 0.5 plus Bc but not greater than 1. So Bc being the ratio of short side to long side of the column. As we are having the square column, both the sides are same. So that BC value will be 1. So 0.5 plus 1 will be 1.5. But here it is mentioned it should not greater than 1. So we need to consider the Ks value as 1 alone. Then this tau c equal to 0.25 square root of FCK for a limit state method. So we are doing the design only with the limit state method. So we need to consider this one. Another case is 0.16 root FCK for working stress method. So this we can ignore. So here in the Excel sheet you can see that allowable shear stress we have mentioned as 0.25 square root of FCK. So considering the Ks is 1, so which is square root of the FCK we had considered in our input as M25, that is 25 Newton per millimeter square, 25 megapascal. So considering this 0.25 with a square root of FCK, we are getting 1.25, which is greater than the actual shear force or shear stress which is occurred, hence it is safe. Similar like for section YY we need to consider the same thing. Here instead of D1 we need to consider D2, and instead of column size we need to consider the drop size, that is the drop phase. Here in the section you can see, so this portion is going to act as a effective two-way shear for this base slab. So instead of CL we need to consider this width of the drop. So width of the drop we already assumed as 1.5 meter here in the foundation geometry. So the same value we need to consider here. So coming to this design bearing pressure we need to consider the same as per the reinforcement calculus consideration, and shear force is V1. Yes, here shear force V2, that is two-way shear, equal to L square minus L1. L1 is that drop width 1.5 meter plus D2 divided by 2 into 2, because there are two number of D2 by 2. So multiplying D2 by 2 into 2, the 2 will get cancelled, only the D2 is going to be available. So L square is a total span minus L1 plus D2 square, will be getting the effective stress area, that is two-way shear stress area, multiplied with the P is the design bearing pressure. We are getting 808295 Newton. That divided by the area, stress area, that is two-way shear stress area along at the section YY. So here D2 we need to consider instead of D1 in our previous at the section XX. So remaining things are same. So it is 0.413 Newton per millimeter square. Again this we need to check for 456 code number, same 0.25 root of FCK. So the value is remain same as per at section XX. So here also this 1.25 allowable shear stress is greater than the actual shear stress, hence it is safe. So this is the two-way shear check calculation. Next we will go to check for bond stress. Coming to check for bond stress, so we need to consider the design bearing pressure as we calculated earlier, 0.37 Newton per millimeter square. Here that maximum shear force we need to calculate. In this we need to consider the same as for one-way shear, where in one-way shear calculation at section XX we had calculated like this: shear force V1 equal to L minus CL divided by 2 minus D1. So this whole length we are multiplied with that bearing pressure. So likewise we need to consider the same here in bond stress calculation also. Maximum shear force is 5000 is a L minus CL is a 700 divided by 2 minus D1. The same multiplication, same calculations we need to consider here for the length, effective length of shear stress. So you can see in the plan view. So this 5000 minus 700 divided by 2 is the area which we got selected here, which is from the face of the column to the edge of the base slab. Again we need to deduct this with the effective depth at section XX, so that the clear span, that is the effective span of the shear, will be from this XX part, which is selected as a dark blue color. So this is a effective span. So that effective span multiplied with the width, that is 5000, the same is multiplied with the design bearing pressure, then we can able to find out the maximum shear force. The only change between this one-way shear calculation and for bond shear is bond stress is, here we had considered only 1 meter, but in that case we are considering total of span 5 meter. So that is a difference. Then the maximum shear force is 309690 Newton. Then we need to refer appendix G. For that, page number 97. So here is a page number 97. So this neutral axis depth factor we need to calculate. XU by D is a neutral axis depth factor equal to 0.87 Fi AST, 0.36 FCK BD. So in the right hand side all the values we know. So Fi is a 415 and AST is a 2813 mm square, that is steel reinforcement area. 25 is the FCK value and B is the 5000 which we had considered here. D is the effective depth. So this 2813 is we had considered as per the reinforcement calculation for compression reinforcement zone for section, critical section XX, 2813.44. So by applying all this value to that equation, we are getting XU by D, that is neutral axis depth factor, as 0.048. So now we need to find out the lever arm distance. So what is that lever arm distance? You can see here in the picture, right hand side. So after calculating the XU by D, which is a neutral axis depth. So neutral axis depth is lies in this red color line. So this is a neutral axis depth XU. So XU by D means it is nothing but the neutral axis depth factor, which we had calculated here, 0.078. So if we are going to multiply this 0.748 with our effective depth, like our effective depth is 476. So then the value of effective depth, neutral axis depth will be 23 mm. So that is what the meaning of neutral axis depth factor. So that our neutral axis is lies in between somewhere here. So to calculate the lever arm distance, so lever arm distance you can see here in the picture J, which is to be calculated from the effective depth, full effective depth minus 1/3 of the XU by D or XU. So XU, why we are considering the 1/3 is it is in a triangle shape. The neutral axis depth, so in the top it is a tension and the bottom it is a compression, or else in bottom it is a tension and top it is in compression, so that stress variation will have in a opposite direction both in tension and compression as seen in here. So that XU is a neutral axis depth. From that we need to find out the lever arm distance. So lever arm distance means we need to deduct this D1 to calculate the lever arm distance. The equation will be D1. So from this picture itself we can able to calculate what could be the lever arm distance. So XU is lies in the triangle shapes, so we need to consider 1/3 from the bottom. So XU divided by 3. So this is the equation to calculate the lever arm distance which we had arrived from the picture showing. So we can also simplify this as we don't have that XU value. So this we can simplify it as 1 minus XU by D1 divided by 3. So what I have done here is the D1 minus XU by 3, I am dividing the entire value, entire right hand side with the D1, so that it will be converted into 1 minus XU D1 by 3. So the same equation we are adopting here. So 1 minus XU by D divided by 3. So now it is very simple to calculate the lever arm distance factor. It's not lever arm distance, it is a factor. So 1 minus XU by D, which we had calculated, divided by 3, we are getting 0.984. So that means the lever arm distance is lying in between. The blue color line is the lever arm distance in the right hand side picture. So it is lying here. So this is what we had calculated here. Now we need to check this allowable bond stress. So for that we need to go page number 44. So here you can see that the design bond stress and limit stress according to the grade of concrete. For us it is a M25. So 1.4 we need to consider. So this bond stress is only for the plain bars in tension. And if we are going to use, as we are using the deformed bars conforming to 1786, then this to be increased by 60%. So this is what increased here. So as per our grade it is 1.4 into 1.6 multiplied. The allowable bond stress is 2.24 Newton per millimeter square. Now we need to calculate the bond stress. So we already calculated the maximum shear force here divided by the lever arm distance factor, and the same to be multiplied with the effective depth D1 and a number of bars. This one is a 14 number of bars we are providing here. So that we get calculated in here in our last video. 40 numbers is required for compression reinforcement at section XX. So that we are considering here. And pi d. So this is simply equation formula, pi d into d multiplied by the shear force. So now we can able to find out the bond stress as 0.94 Newton per millimeter square. This bond stress is less than the allowable bond stress which is specified in class 26.2.1 of IS 456. Then we can call it as safe. So with this, the foundation pad type 1 pad and chimney foundation type 1 pad and chimney for transmission line tower foundation is get completed. Thank you. Look description for more related videos. Subscribe to this channel for more updates.